Hello. In this video, we are going to use our knowledge of exponential growth functions to explore a particular example of a situation where some quantity is growing exponentially. We will set up a model, an appropriate function that represents this situation. We will solve for the arbitrary constants that appear in that model to come up with a function, and then we'll use that function to answer some questions and better explore this specific example. And then at the end, I will use this example to introduce and discuss the notion of a doubling time for an exponential growth function. So the example we're going to explore is a town whose population is growing. Let's say in the year 2000, we have 10,000 residents, and let's say somehow we know that it's growing at a constant rate of 6% per year. So after this video, I'm hoping that you will, in the future, look at that phrase and recognize that that means exponential growth. And even more specifically, I hope that in the future you will recognize that this is going to lead to an exponential growth function whose constant b, that multiple in the exponent, is 0.06 because of that 6%. That's another way to write 6% as a decimal value, 0.06. So what we're going to do is come up with an exponential function that describes this population growth over time. And then we're going to use that to answer some questions. So right now we're going to address a couple of the lessons for this example, which is choosing an appropriate type of function to model this situation, choosing and labeling and solving for the variables in that function. And then as we go and answer the rest of the questions, we'll address some of these other points that I have outlined here. So that constant relative growth rate of 6% per year, that's another way of saying what I have written here, that the derivative of the function divided by the function itself is 6%. It's constant, that number. Or in other words, that the derivative of a function is a multiple of itself, specifically 0.06 times the function itself. Now, based on the last video, we already solved a situation like this type of differential equation, and we came up with an exponential growth function. Specifically, in the previous video, we showed that this type of differential equation with a b as an arbitrary constant instead of that specific number 0.06, but with a function whose derivative is an arbitrary constant b times itself, that led to the function being a multiple of e to the bx. And so now I'm just going to take advantage of that work that we did in the previous video, and in the future you can do that too. You can recognize that this constant relative percentage growth rate causes exponential growth of this form. And now we're actually going to use one other bit of information. We're going to use this given initial value that the population was 10,000 residents in the year 2000 to come up with the value of A. That's going to tell us where that 10,000 is coming from. But be careful, I have to pay attention to how the variables are defined. And I have chosen in the setup of this problem to say x is the number of years after 2000. Now that's helpful because that tells me that f of 0 has to equal 10,000. So in other words, when I plug in 0 for x, and set that equal to 10,000, and there's me plugging in the 0 into the function, then I'll get a times e to the 0, which is just a times 1, which is just a, and that has to equal 10,000. And so now I can see where I'm getting this function f of x from the given information. In fact, in general, this is a pattern you will notice and you can take advantage of and just say, we know how this works. The initial population at time x equals 0 is that multiplier a in front, and that constant relative percentage growth rate of 6% tells me that value b of 0.06. So now that we have that function, let's start to answer some questions about it to try to better understand exponential growth. Let's use this function to estimate the population in the year 2020. So that's going to tell me that I need to use x equals 20, because remember that x is the number of years past the year 2000. So this first question is asking me, what is f of 20? What happens when I plug in 20 for x? So there's me plugging in the value x equals 20, crunching some numbers on my calculator, and saying that this output is approximately equal to 33,201. That's what the squiggly equal sign there is. That's not my bad handwriting, although I admit that I do have pretty bad penmanship. So I've rounded off. It's 33,201.169, blah, blah, blah. But this is, there's no way to believe that the real world population is actually following exactly 6% every year, so it's okay to round off like that. My next question, when will the population hit 40,000? That's asking me to do something slightly different with the function. Instead of plugging in an x value because I had a year, like in the first part, I'm now going to be setting the function output equal to 40,000 and then solving for x. There, I've set up that equation. The output population of 40,000 is equal to, and then there's the function f of x itself. First thing I'm going to do is divide both sides by that 10,000. That's where I'm getting the 4 on the left side that I'm about to write. The variable that I'm trying to solve for x is stuck up there in the exponent of something, so I'm going to apply a logarithm on both sides. And because that's an exponent base e, I'm going to apply a natural logarithm. So I'm going to see ln of 4 equals, now what's the natural log of an exponential thing like that? It's just the exponent itself. So that's going to turn into just 0.06x. And then finally I'll be able to say x is log of 4 over 0.06. I crunched some numbers on my calculator and I found that that's approximately equal to 23.1. And so, in other words, my answer to the question is that this population will hit 40,000 in the year 2023. Again, remembering that x is the number of years past 2000. Look at this work that I just did for this problem. What do you think would be different if I tried to solve for when the population reaches 80,000? Well, that would change the 80,000, it would change this, and it would make this 4 into an 8 instead. That's really the only difference. It's going to change the final number I get in the year, but all the other steps are exactly the same, so I'm not even going to bother rewriting what that works out to be. I can just tell you what the final results are. And then the same for the 160,000, that would be 160, it would turn into a 16, and so on. And so I'm going to open a new page and write down the results of those. So here are the results from those 3 questions. The population will reach 40,000 in the year 2023, and that comes from an x value of 23.1 or so. The population will reach 80,000 in 2034. That comes from an x of 34.6 or so. So I rounded that down to 34. More specifically, you can say the population will reach 80,000 a little bit past halfway through the year. And then the population will reach 160,000 just after the beginning of 2046. So I want to make a comment about these values. I didn't arbitrarily pick 40, 80, and 160. You may notice that these are double each other. I kept multiplying by 2 because I'm showing you that there's a pattern. There's something specific happening here. Because the difference between these values here, the 23.1 and the 34.6, or more specifically, I wrote out the natural log exact expressions that they came from. The difference between those, if you subtract those exact values, you get a difference of around 11.55. And in fact, if you do the same thing down here with the 80,000 number and the 160,000 number, you get exactly the same difference, and that's not a coincidence. Maybe even a better way to note this is that the number up here, that 23.10, and the 46.2 down there, that's exactly doubling, a times 2. That value at the bottom is exactly twice the number at the top. And a way to see that algebraically is what I've written down here at the bottom right, to show that that number in the numerator of the expression at the bottom down there, that natural log of 16, that's exactly double the natural log of 4 up there using this property of exponents and natural and logarithms of any base that we know. So in fact, it's not a shocker that that number at the bottom is exactly double the number at the top. So what I'm trying to demonstrate with this example, this set of questions, is that there's something interesting about exponential growth where the output being multiplied by a specific number comes from the input increasing additively by a specific number. So every time I double the output population, when I go from 40 to 80 times 2, and then I go to 160 times 2, each of those times I'm multiplying the output by 2. The input is increasing, the corresponding input is increasing by adding a specific number, and that's what that difference of 11.55 is. And that's actually going to lead us nicely into the next topic, which is something that isn't inherent to this particular example, but all exponential growth functions, which is an exponential growth function has an inherent doubling time. To make the output of the function twice as big, you have to increase the input by adding a specific number. And it doesn't matter what the starting value was, it's always the same input value. So let me set up an equation that we can solve to try to explore what's happening with our particular situation here. As a reminder, here's the population growth function f that we found, and we know that the input at time 0 in the year 2000 was 10,000. So I might wonder, how long does it take to double that population? Here I have set up an equation that represents that question. How long will it take to double that initial population? Well, I'm going to use 20,000 as the output because I want to double the initial value of 10,000. And then when I say how long, I'm asking for time, so I'm going to try to solve for that x that's up there in the exponent. Now this algebraic work we're about to do is almost exactly the same as everything we did on the previous couple of slides. I'm going to divide both sides by 10,000, so I get 2. I'm going to apply a natural log on both sides. And then I'm going to divide by that b value of 0.06. And turns out that's approximately 11.55, and that should look pretty familiar considering what we just did on the last slide. That was that common difference between all of those x values, all of those years, where I kept asking when does the population reach a particular output, and I kept asking for double the output of the previous question. And so that 11.55, that is the doubling time of this function. That's how long it takes to double the population. I can see from the work on this slide that that's the amount of time it will take to go from 10,000 to 20,000. And then based on our work on the previous slides, that's in fact exactly the same amount of time it takes to go from 40 to 80,000 and from 80 to 160,000. It didn't matter where I started, it will always take that 11.55, that same amount of time to double the current population, no matter what it was to begin with. That's what I've stated in this theorem box up here. In this case, that's the role of that little h that I have in the theorem. That's the doubling time. You can always solve for it by doing something like I did here, setting up an equation, setting the exponential growth function equal to twice its initial value, and then solving for the input x that would make that happen.